All right, so let's review some past exam questions on momentum and Newton's laws. So we've got a ball of mass 500 grams thrown against the wall. The ball hits the wall horizontally with a speed of 6 meters per second and it rebounds at 4 meters per second. The total contact time 0.12 seconds. What is the average force acting on the ball during the time of contact? Okay, so I'm going to use Newton's second law, which states that resultant force is rate of change of momentum. The mass of the ball doesn't change, so we can kind of take that out, factorize that out of the expression. But the key is that the velocity is in a different direction. So I'm going to say going to the left is negative, so that's why it's -4. And then to calculate the change, we do final minus initial. That gives us a total velocity change of 10 meters per second. Divide that by 0.12 times by 0.5 gives us a force of -42 newtons, which means 42 newtons to the left. Remember, I defined the left as being negative earlier. So that's clearly option C. Okay, so two equal masses P and Q collide elastically. P has initial speed u, and Q is initially at rest. The diagram shows the direction of movement of the masses following the collision. After the collision, P moves with speed v1 at an angle theta, Q moves with v2 angle alpha. Which statement is correct? So I'm going to apply conservation of momentum using the initial direction of P as the direction I'm going to apply conservation of momentum to. Because remember, momentum is a vector quantity, so we need to apply it all in one direction. So the initial momentum is simple, that's just mu. And then the component of P's momentum in that direction would be mv1 cos theta, and the component of Q's momentum would be mv2 cos alpha. We can also apply conservation of momentum in the kind of the vertical or upward direction. So P initially had no momentum in that direction, so the total momentum in that direction is 0. The component of P's momentum in that direction is mv1 sine theta. The component of Q's momentum in that direction is minus mv2 sine alpha, because it's in the opposite direction downward. And so we've got our two expressions from conservation of momentum there. Now we can see that the first one matches up with option B. The diagram 2 shows two trolleys, X and Y, held stationary, and that's going to be important, I think, connected by an extended elastic cord. The mass of X is twice that of Y. The trolleys are released at the same instant and they move towards each other and stick together. That's going to be important too. Just before the collision, the speed of X is 20 centimeters per second. What is the speed of Y just after the collision? So I'm going to explain to you how I think about this. So they're initially stationary, so total momentum is 0. At the end, they stick together, and the total momentum must also be 0. Therefore, Y must be traveling at 0 meters per second. The reason for this is because with a stretched material, that's what we call an internal force. So yes, it's going to increase the momentum of X to the right, but it's also going to increase the momentum of Y to the left, and it's going to make them so that the momenta are equal and opposite, which is how they can become stationary at the end. Okay, so a body of mass 8 kilograms moves at 5 meters per second, collides with a stationary body of mass 12 kilograms. They both move off with the same velocity. Which statement is correct? Okay, so we can apply conservation of momentum. Total momentum before is 40. We can write an expression for the total momentum afterwards with their velocity being the same. And then we can see we can solve V is 2 meters per second, which is going to be in the positive direction. Okay, so moving on to some longer questions. So we've got a motor car of mass 1200 kilograms. The engine and transmission provide at the wheels a constant force of 5 kilonewtons or 5,000 newtons at speeds from 0 to 10 meters per second. Neglecting frictional forces, calculate the initial acceleration of the car. So we're just going to use F equals ma. For F divided by m gives us the acceleration. And time taken to reach 10 meters per second, so we're it says that that force is the same the whole time, so the acceleration is going to be the same the whole time. U is 0 because we're told it starts at rest, so we can quite simply find the time taken. Above 10 meters per second, the force is no longer constant, and now we've got a constant power. Calculate the force developed at a speed of 20 meters per second. So, P equals FV is the equation we're going to use. So the force is going to be P divided by V, 2,500 newtons. Fairly straightforward. So draw on the axis a graph of force against speed for this car, explaining how you obtained the shape of your graph. So initially, for the first period of time, we had got that the force is constant. And then we've just seen that once we're up to 20 meters per second, the force is 2.5 kilonewtons. And remember that force and velocity are inversely proportional if power is constant. So that's why the gradient decreases and we get that curve. Okay, so a skydiver mass 75 kilograms jumps out of an aircraft at level flight at a great height above the Earth's surface. Calculate the gravitational pull of the Earth on the skydiver. So we're basically calculating the weight force there. Okay, so initially the skydiver falls faster and faster, accelerating downward. Explain in terms of the forces acting why the downward acceleration decreases as the speed increases. So the skydiver has a constant weight force acting down, so it's not going to be caused by that. However, as the velocity increases, the skydiver is going to collide with more air particles each second, and that's going to cause an increase in the force of air resistance acting upwards. And that is going to decrease the resultant force and therefore decrease the acceleration downwards. So only a few seconds after leaving the aircraft, the skydiver is falling at a maximum speed of 50 meters per second. Explain why you reach a steady speed. Well, eventually the rate of change in momentum of the air particles colliding with the skydiver will be equal to the weight force acting downwards on them. Those two forces cancel out, giving you a resultant force of 0, and therefore the acceleration is 0 and the velocity is constant. To land, the skydiver opens a parachute. When he does this, the vertical speed decreases rapidly from 50 meters per second to about 5 meters per second, and then falls at a steady speed. Explain in terms of the forces acting why he decelerates rapidly when the parachute opens. So that's going to massively increase the area that is moving through air particles. So that's going to increase the rate of change of momentum of air particles because there's more of them colliding every second. And that's going to mean the air resistance is much bigger than the weight force. The resultant force, therefore, must now be upwards, and that's why the skydiver's velocity decreases until rate of change of momentum of air particles is once again equal to weight force. In terms of why it falls at a smaller steady speed than before the parachute was opened. So if you have a much bigger area, that means you can have more air particles colliding every second. So that means the impulse we actually need from each air particle can be smaller in order to achieve the same total rate of change of momentum that we needed with a skydiver without a parachute. And so you can get this lower impulse from much slower skydiver speeds, which is why it's now 5 meters per second instead of 50. Okay, so the question is about a rocket leaving a distant planet. We've got a rocket mass 10,000 kilograms and its initial acceleration is 3.1. What's the resultant force? F equals ma will tell us that, fairly straightforward. Okay, so then moving on, we've got a thrust force of 7.5 times 10 to the 4. What must the rocket's weight be? Well, the thrust minus the weight force must be equal to the resultant force, so therefore the weight force must be the thrust force minus the resultant force. So then if we want the gravitational field strength, we just divide that by the mass of the rocket, giving us 4.4 meters per second squared, or that's usually, because it's field strength, usually expressed as newtons per kilogram, but newtons per kilogram and meters per second squared are in fact the same unit. So a body of mass m is moving with velocity v and is to be stopped in a straight line by applying constant braking force F. Use Newton's laws to show that momentum of the body equals Ft, where t is the time it takes the body to stop. Okay, so what we can do is we're going to use Newton's second law. Newton's second law states that resultant force equals rate of change of momentum. And I'm going to take the small period of time across to the left-hand side, and I'm going to integrate with respect to time on the left, because we've got delta t, and with respect to velocity on the right, because we've got delta v over there. For integrating with respect to time, we're going to start this process at time equals 0 up to some time t, and we're starting with velocity v and ending up with a velocity of 0 because we're stopping it. So we're told that force is constant, so integrating force with respect to time is just going to give you Ft. Integrating 1 with respect to dv just gives you v, but we're doing it between the limits of 0 and v, so we're going to get 0 minus mv, which is just equal to minus mv. So essentially what that means is the object must have initially had momentum of fv, so then you lose mv and you have no momentum at the end. Kinetic energy we're going to do in a similar way with one additional step. So we're going to multiply both sides by a small change in displacement delta s. And the reason I've done that is that's how we turn force into energy. We find the area under a force displacement graph, or we integrate force with respect to distance. And then at this point, there's a sneaky trick, because I'm going to swap the delta v and the delta s over, and delta s over delta t is just equal to velocity. So at this point, I'll now integrate on both sides. We're going to say the starting point has a displacement of 0 up to some point s, starts at velocity v to stationary. The left hand side, force is constant, so again becomes fs. The right hand side, v becomes half v squared times by m, so half mv squared, so it's 0 minus half mv squared. So the object must have initially have had kinetic energy of half mv squared and then lost all of that when it became stationary there. Okay, so let's now actually put those expressions to use, because we've now been given a mass and a velocity and a distance. So we can take displacement to the other side, plug our numbers in, and we can see the force is equal to 4.9 meganewtons, and it's negative because it's acting against the motion of the object. And if we want time, we can use the expression we generated. We know mass, we know velocity, we now know what the force is because we just calculated it, giving us a total of 250 seconds.